In our next question now, we have some ice floating on a freshwater pond. Maya and Kevin are sitting on the ice block. We know that Maya has a mass of 30 kilograms and Kevin has a mass of 37 kilograms. We're given the buoyant force on the ice, 13,251 newtons. This sort of implies that as we go through our calculations, we should keep 5 sig figs on our calculator because it's given with 5 sig figs. Okay, question 25. True or false? The pressure at a point directly beneath the ice is the same as the pressure at any other point in the pond at the same depth. If we wish, we can do a quick sketch here. So let's say this is our pond. This is our pond level, and this is our block of ice. And I suppose we can put Maya and Kevin on there too if we wish. So our question is saying, is it true or false that the pressure here at point A is equal to the pressure here at point B, where A and B are at the same height? Well, A and B are at the same height in the same static fluid, therefore they have exactly the same pressure. So this statement is true. And that's Pascal's principle. Whenever two points at the same height in the same fluid will have the same pressure. All right, question 26. What's the volume of the ice block? Well, it's a little bit hard to know what to do right off the bat. So when in doubt, why don't we draw a free body diagram? Let's look at the forces. Let's bring in our buoyant force because we know the buoyant force has something to do with volumes. Okay, so we'll start with the free body diagram. Here's the water. Here's our ice block. Here's Maya. And here's Kevin. So if we're going to draw our forces, let's see what we'll put on here. We know that the ice block has some mass, so we have the weight of the ice pushing down. If we consider the whole as Maya, Kevin, and the ice as a whole system, then they're kind of all one object, then Maya's weight also pushes down. And Kevin's weight also pushes down. All right, well, what keeps them afloat? That would be the buoyant force. So now we've got our free body diagram done. Our next step is to write Newton's second law. The net force in the y direction is the mass of the whole thing in the mass of the whole thing, so Maya, Kevin, and the ice, times the acceleration in the y direction. We know it's not bobbing up or down, so that's going to be 0. So then our net force is the buoyant force, FB. Subtract the weight of Maya, mass of Maya, times G. Subtract the mass of the ice, times G. Subtract the mass of Kevin, times G, equals the mass of everything times the acceleration in the y direction, which is just going to give us 0. Okay, what we're trying to find now is the mass of the ice block. So the mass of the ice block times G is the buoyant force, minus the mass of Maya times G, minus the mass of Kevin times G. If we want to solve for the mass of the ice, we have to divide everything by G. So the mass of the ice is the buoyant force divided by G, minus the mass of Maya divided by G gives us the mass of Maya, minus the mass of Kevin divided by G gives us the mass of Kevin. Our buoyant force was 13,251 newtons. Divide that by G, 9.81 meters per second squared. We're subtracting the mass of Maya, that was 30 kilograms, and we're subtracting the mass of Kevin, 37 kilograms. Gives us the mass of the ice, 1,283.8 kilograms. I am going to keep my 5 sig figs here for a minute. All right, I found the ice. I wasn't asked for the ice, I was asked for the volume of the ice block. I've got a hint here, I'm given the density of ice. So here I might remember that density is mass divided by volume. So density of ice is mass of ice divided by volume of ice. I know the mass of the ice, I know the density of the ice, so I can go ahead and solve for my volume of ice. That's going to be the mass divided by the density. 12,000 or 1,283.8 kilograms divided by 917 kilograms per cubic meter gives me a volume, and here I'll round to 4 sig figs, 1.40 cubic meters. So that's the volume of that block of ice. Okay, let's see what happens with Kevin and Maya next. So the next thing that happens now is Kevin sees a shiny gold bar sitting at the bottom of the pond at a depth of 2.3 meters below the surface. Kevin dives down to get it. What's the pressure where Kevin picks it up? So let's just do a quick sketch of what's happening there. There's our water. Here's our gold bar right down at the bottom. We're trying to find the pressure right here. We know that the depth is 2.3 meters. We might call that H. So I'm going to call this point 2 down at the bottom. Up here where the water meets the air, I'm going to call that point 1. I know that the pressure at the bottom of a column of fluid, P2, is equal to the pressure at the top plus rho times G times H. My pressure at the top, P1, that's atmospheric pressure, so it's PATM. Notice we're asked to answer here in units of atmospheres. So my P2 is going to be P1 plus rho times G times H. Rho refers to the density of water, 1,000 kilograms per cubic meter, times G, 9.81 meters per second squared, times H, 2.30 meters. That gives me P1 plus, when I do this calculation, I get 22,563 pascals. Now, I can't add an atmosphere and a pascal. I have to convert this to atmospheres. So I'll apply my conversion factor of 1 atmosphere divided by 1.01 times 10 to the 5 pascals. This part turns out to be 1.22 atmospheres. Oh, sorry, this part turns out to be 0.22 atmospheres. So this is 1 atmosphere plus 0.22 atmospheres. So my total pressure at the bottom is 1.22 atmospheres. Okay, what's next? At the moment that Kevin leaves the ice block, so Maya and Kevin are sitting on it, Kevin jumps off to grab the gold. Which of these statements is true about Maya's acceleration? Does she accelerate upwards or downwards, or she doesn't accelerate up or down at all? This is kind of an interesting question. Let's think about what's happening. So before Kevin hops off, we drew a free body diagram, and we had that the net force was equal to 0 and the acceleration was equal to 0. Nothing was moving up or down when they were just sitting on that ice block. They were just floating there. So as Kevin steps off, well, what's happening is that his weight is no longer pushing down. So as he's stepping off, the total amount of force upwards now becomes greater than the total amount of force downwards. That downward force decreases, but as he's stepping off, the upward force doesn't change. So as he steps off, there's more up force than down force, so the acceleration is going to point up. So that means choice A is correct. And that probably matches your everyday experience. Ice will bob up if you take a little bit of weight off of it, or something underwater will bob up when you take some weight off of it. Okay, question 29. What is the magnitude of the buoyant force on Kevin when he is underwater? Assume that Kevin has an average density of 985 kilograms per cubic meter. This is kind of an interesting question, and you have to remember Archimedes' principle when you come to this question. And Archimedes' principle says that the buoyant force, Fb, is equal to the weight of displaced fluid. So if Kevin is underwater, we have to ask how much volume of fluid is he displacing. So now the weight of our displaced fluid is going to be the mass of the water, because the fluid being displaced is water, times G. The mass of the water is going to be the density of water times the volume of displaced fluid. That's the same as the volume of Kevin. So Kevin pushes his own volume of water out of the way. I'm going to multiply that by G. Okay, we're kind of getting somewhere now. We know the density of water, we know G. We don't know the density of, or we don't know the volume of Kevin yet, but we do know Kevin's density and we know Kevin's mass. So let's remember here that density of Kevin is mass of Kevin divided by volume of Kevin. That tells us that Kevin's volume is going to be Kevin's mass divided by Kevin's density. Okay, let's put this together in our expression for our buoyant force. So now our buoyant force was the density of water times the volume of Kevin, which is the mass of Kevin divided by the density of Kevin, times G. Okay, I think we are good to go at this point. Density of water is 1,000 kilograms per cubic meter. Mass of Kevin was 37 kilograms. Density of Kevin, 985. And G, of course, is 9.81 meters per second squared. Put all this through the calculator and we get a buoyant force of 368 newtons. So that's the upward force on Kevin when he's swimming around underwater. And all of Kevin is underwater at this point. Okay, let's go on to the next question about Maya and Kevin. So this question is now about water levels. When Kevin gets back to the top of the ice block with the gold bar and he's sitting there with Maya, what happens to the water level in the pond compared to when they were sitting there but the gold was at the bottom of the pond? So we have two different situations here. First, let's say this is our pond. Here's our gold bar at the bottom. Here's our block of ice. Here's Kevin and Maya. Okay, so that's situation one. Situation two, we've got our ice block, and this time on top of the ice block is Kevin and Maya and our gold bar. So what happens to the volume, to this water level as we go from here to here? And this is a different situation. We went through this in our lectures and I did a PhET simulation and we took bricks and wood in and out of water and we looked at what happens to the water level. When our gold bar is completely underwater, it displaces its own volume of water. So the water level pushed out of the way, the amount of water pushed out of the way is the same as the volume of the gold bar. Displaces own volume. That's very important. So whatever the volume of the gold bar is, that's how much gets pushed out of the way. Up here now, though, it has to displace enough water to keep it afloat. So rather than displacing its own volume, it displaces more or less its own weight. So this time, the buoyant force FB is equal to the density of water times the volume of the gold bar times G. In this picture, the buoyant force has to offset the weight of this bar. So in this picture, the buoyant force is equal to the mass of the gold times G, because that's how big the buoyant force has to be to keep that afloat, equals density of gold times the volume of water displaced. Density of gold times the volume of gold times G. So this one is going to displace more water. Because we have to push way more water out of the way in order to hold that up. If we displace more water, the water level is going to increase. Okay, so if we take something heavy out of the water and we make it float, we push up the water level. All right, next question. Maya and Kevin climb off the ice. They take the gold with them. What percentage of the ice block is going to be above the water? So there's nothing else on top of the ice. How much of the ice now is above water? Let's draw a new free body diagram. Let's put in our ice block. And let's make sure we know what the question is asking. So this much of the ice block is below water. This is the volume of water displaced. We care about the percentage that's still above water, and we'll notice here that the amount that's above water plus the volume displaced, the amount below water, that's going to be the volume of the whole ice block. Okay, let's go with a free body diagram. The upward force is the buoyant force. The downward force is the weight of the ice. Our Newton's second law says that the net force in the y direction is the mass of the ice times the acceleration in the y direction. The buoyant force, subtract the weight of the ice, is the mass times the acceleration, which is 0, just gives us 0. Our buoyant force is the density of water times g times the volume of displaced fluid, that's the amount of ice that's underwater. Subtract the mass of the ice times g equals 0. I'm trying to find the volume of displaced fluid, so that's going to be the mass of the ice times g divided by the density of water times g. Notice that my g's divide out. Mass of my ice, I found that in an earlier question, 1,283.8 kilograms, divided by density of water, 1,000 kilograms per cubic meter, to give me a volume of displaced fluid, or the amount of ice that's underwater, of 1.2838 cubic meters. Okay, now this isn't what I was asked for. I was asked for what percentage is above water. So the amount above water would be the volume of the whole ice block, subtract the volume that's below the water. So 1.4 cubic meters minus 1.2838 cubic meters to get 0.116 cubic meters. So not much of it is above water, but some of it is. Now, we weren't asked for the volume in cubic meters. We were asked for it as a percentage. So to find our percentage, we will do the volume above, divide by the volume of the whole ice block, and we'll multiply that by 100%. And what we get for our answer is 8.29%. That matches what we know about ice, that only about 10% is above the surface level of the water when we have ice floating. Okay, one last question. So now Kevin and Maya are sitting on the shore. They've got their gold bar and they're watching the ice melt. What happens to the water level of the pond as the ice is melting? So this is a pretty interesting question. And let's see if we can think about it. The answer is, as the ice melts, it turns back into water. So it means that the water level is going to be exactly the same. There's no change because the ice is made out of water. Okay, so the problem starts before we have any ice in the pond at all. The pond is at a specific level. That's where we start. Okay, the next thing we do is we add the ice block. So we add the solid ice block. What happens when we add the solid ice block is it pushes an amount of water, V displaced, that we calculated in that previous problem, 1.2838 meters cubed. It pushes that much water out of the way. The pond rises. And the pond rises because that much water was pushed out of the way. If we took the ice block back out, it would go back to its specific level. Okay, now what happens as the ice turns into liquid? Okay, two things are going to happen. If the ice is now liquid, it's not pushing the water out of the way anymore. It can't push on it because it's water, but it does add volume to the pond. It adds its volume of water to the pond. So it adds liquid to the pond. How much liquid does it add? Well, the volume added will be the mass of the ice divided by the density of water. And I'm dividing by density of water because the ice turns into water. It has the same mass, has the same number of molecules, but as it melts, it has a new density. So the total volume of liquid added to the pond is whatever the mass of that ice chunk was, divided by its density when it's water, 1,283.8 kilograms, divided by 1,000 kilograms per cubic meter to get 1.2838 meters cubed. Same. So when it's ice, it pushes that much out of the way, but if it turns into liquid, it adds this much to the pond. So overall, the water level doesn't change a bit, it stays exactly the same.